Okay, so let's continue. Okay, so before the break, so we were looking at how to find the hyperparameters using validation sets, right? So now, we also had a question how to pick, how to choose the size of the validation set. So now there is also another question which is very related and useful, important, which is how to pick the validation set itself, right? So you have a training data set. Now, how do you sample the validation set from this training data set, right? So what if by unluck, the 20% that you are sampling is happens to be the bad 20% or not representative of the test set, right? So in some sense, as if you remember, we have train, valid, and test set, and the test set is basically the proxy for real life performance, and the validation set is a proxy for test set, which means we want the validation set to be as close as possible to the real life distribution as possible, right? So what if you got a skewed distribution, or something that is not representative, right? So then the choices that you're going to make might give you low validation error but high test error, right? So how do we avoid that issue, right? So this is where we are going to slightly generalize this idea of splitting data into train, valid, and tests. Okay. Now, first of all, this idea of using a validation set to choose hyperparameters, right? So this also has another name, which is cross-validation. Okay. So what is cross-validation? Cross-validation is basically taking the data and dividing it into train and valid, and use the validation set to pick the best model. Okay. Now, as I mentioned before, what if this split is a bad split? So, well, first of all, we can never be sure that this is a bad split, right? So, for example, let's say the validation error is good, but the test error is so high, then you can guess that it is a bad split, right? But you cannot be very sure that it is a bad split, right? So now to avoid these issues, one can do k-fold cross-validation. Okay, so what is k-fold cross-validation? So the idea here is to take your training data, and instead of splitting it into 80% train and 20% valid, I'm going to split my data into k equal folds. Okay, so I'll divide the data into maybe 20%. Okay, and each of this 20% they're going to call as fold 1, fold 2, fold 3, fold 4, fold 5. Okay, now I'm going to do the cross-validation process 5 times. Each time I'm going to consider one part as the validation and the rest as training. Okay, so basically I'm averaging over 5 different train valid splits. Okay, so how do I do that? So the first experiment, I'm going to consider this to be the valid and this to be the train. Okay, this is the first fold. In the second fold, I'm going to consider this to be the valid and the rest to be train. Okay, and third fold, this is valid and the rest is train. Okay, and fourth fold, this is valid and the rest is train. And finally, this is valid and the rest is train. Okay, now I get 5 validation performance numbers, right? Now I can average these 5. Now I can do this whole process for different values of lambda. Whatever value of lambda which has the best average performance with K4 cross validation, that is my best lambda. Is that clear? Now, as you can imagine, this is a very costly process. So instead of just, first of all, finding hyperparameters itself is a costly process, right? Like, because to find a hyperparameter like lambda, you might need to try 100 different lambda values and do your training process 100 times and compute the validation performance 100 times, right? Now, this means that if you have 100 possible lambda values, you do experiment 5 times each. So you do 500 experiments and you take an average of all these 5 experiments for every possible lambda, and then you pick the best lambda. Okay, so this is a costly process, but often this results in more like statistically significant results. Yeah.
Is there a way of calculating or at least in a range of content, but just blindly guessing?
That's a good question. So, well, probably it's a discussion for the future, but I'm going to give you some like ideas. So, first of all, for every model that we are going to see, we will discuss the hyperparameters of the model, and often there is a good range. Okay, so for example, if you take lambda, right, it's a real number. The range is infinity, right? Like, so of course we will not try infinity. So we will only pick a small range and then try different values in that range. Okay. Now you can also come up with heuristics for picking this range. Like, for example, okay, now I'm going off the notes. So for example, let's say this is my hyperparameter. Okay, I can randomly pick, let's say 4 values and find the performance for these 4 different lambdas. Okay, now I will find that this is too high, this is too high, which means probably my good range is here. So then I can try even more lambdas here. I can maybe try here, 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 and then I find that this is a good range. And then again, I try different lambdas here. So you can do this iterative process, okay, of like you can do these kind of like binary search or like some other complex form of search. And there are also many other ways of doing like finding this lambda. And there are also ways to learn this lambda, like basically like you're learning the hyperparameter. Probably we will discuss these things in like very late if we have time. So for now, we will not touch hyperparameters. Okay, we will just focus on the parameters. Was there a question? Okay. Okay. Now there is also an extreme form of this K-fold cross-validation, which is called leave one out cross-validation. Okay, which is often common when you have really small data sets. Okay, sometimes let's say it could be a medical application, or like there are like many applications where data points are costly. Okay, so for example, let's say you are collecting data from patients, and your features might be some costly tests, like a test which costs a blood test which costs $1,000. Okay, and not every patient is ready to do this $1,000 test, right? Like, so you're going to have very limited number of data points. When you have like very few data points, then let's say you have only 20 data points. Splitting 80-20 percentage is going to lose you a lot of data points, right? You just have 20 data points. In this case, it's very common for people to use leave one out cross validation, where if you just have 20 data points, you use 19 for training and 1 for testing. Then another 19 for training and 1 for testing. Like you're leaving 1 out. Okay, so it's common when you have really small data sets. Okay, so far we have seen 2 solutions for overfitting. Can someone remind me what are these 2 solutions? What was the first solution? More data points. Okay, what is the second solution? Like adding a regularization, right? So for people in Zoom, I do read your chat, so you can answer in chat. Okay, so now in this particular example, we knew that the real data, like the real function that we are trying to fit, is a 3-degree polynomial, right? So 9-degree polynomial, we can start with a 9-degree polynomial and do regularization, so you fit a 3-degree polynomial. But what if I don't show you the true function, and the true function is a 15-degree polynomial? So can you start with a 9-degree polynomial and add regularization? Is it going to help you? So regularization is going to make things worse here, right? Like, so because the real polynomial is 15 degree, you have a 9-degree model, you are already having a low capacity model than what is required. So regularization is not going to help you. So that's more realistic scenario, right? Like in this is like, we are still in a synthetic setting where I told you what is a true function. But for some practical data sets that you're going to use in your assignment, you don't know the real function. So then how would you pick the degree? Any suggestions? Yep.
Try with the different degrees and try to pick the best one.
Try different degrees and find the best one. So then what is this degree, right? So this degree itself is a hyperparameter, okay? So the third solution is to try different values of m and select m based on the validation set, okay? So this is also model selection, but we are not doing regularization here. You just try different values of m, do normal regression, like without regularization, okay, and pick whatever value that works best, okay. So in some sense, m is also a hyperparameter. Is that fine? Okay, so that concludes our second example. Like, okay, so the synthetic example. So now with this introduction, I think I have given enough introduction. So we are going to look at the general machine learning pipeline. Okay. So normally, for any problem that you are going to face, okay, the first step is to define the input and output, X and Y. Okay. You need clear input to the system and output to the system. So then you're going to collect examples to solve this task. So collect examples for the task. Okay. So then you're going to divide the examples into train, valid, and test set. Okay. So then you will normally do some data pre-processing. So the raw data that you have might not be suitable to directly feed to the model. So you have to do a little bit of pre-processing, okay? So for example, let's say you're using linear regression for weather prediction, like whether it is going to, let's say I want you to develop a system which will predict whether it's going to rain or not, okay? And let's say there is one feature, let's just call it humidity, which has low, medium, high. Now, can I feed in these English words low, medium, high to linear regression model? So the linear regression model that we have seen takes only numbers, right? So then you're going to do a little bit of pre-processing. You're going to call low as 0, maybe medium as 1, high as 2, and so on, right? Like, so you might need to do such pre-processing to the data so that it fits the model, or it fits the input to the model, okay? So then you define your model, okay? So you have to decide which model you're going to use. Now this model will consist of parameters and hyperparameters. Okay, so for every model, you should know what is the parameter and what is the hyperparameter. Okay, then the next step is to define the error function or the loss function that you want to minimize. Okay, so once you decide the error function, now you have a valid objective function, right? Like like you have a valid mathematical formulation. Now you can just minimize that. Okay, so but we also have the issue of hyperparameters, right? Like, so what you're going to do is, like, for different values of hyperparameters, okay, you learn the model by minimizing the loss function, okay, and you compute the validation performance, okay, and you pick the best model based on validation performance, okay. So finally, you test the model with test set. Okay. So this is the whole pipeline. So you start with first definition of the task. The task has some input X and output Y. And you collect examples, you divide the examples, you pre-process, okay? So this all are like your initial steps. Once you finish that, that is where the model comes in. Like, so you decide a model. What are the hyperparameters and parameters of the model? Like, so, and you also define an error function to minimize so that you can find the parameters. And you do model selection based on hyperparameter selection based on the validation set. And finally, you compute the test performance. Yeah, question?
If you have multiple hyperparameters, do you need to create two validation sets, or do you like try all the combinations?
All combinations in same validation set. Okay. Now, there are many important steps in this pipeline. Okay. First of all, this is the good place to introduce the scope of this course. So in this course, we are not going to focus on all these parts of the pipeline. Okay. Now, in fact, one thing I want to highlight is these are really important steps, okay, about the data, which we will not cover in this course. Okay. So this course is more about the models. So we will here and there we will talk about data, but we will not talk about data pre-processing or like how to collect data and so on. Like, so these are normally covered in a data science course or a data mining course. Okay. However, you will do some data pre-processing in your assignments for exposure, but we will not focus on this part. Okay. On the other hand, like what we are going to focus extensively in this course is the second part. Like we will talk about like how to define your model, like and how to learn the parameters and hyperparameters of the model. What are the various error functions and loss functions you can use, okay? And how to minimize your loss function, given that you have chosen a loss function, and how to do model selection. So these are the kind of things that we are going to discuss in this course, okay? However, I think if you are interested in the data aspect of the machine learning, there are standard data mining textbooks. I believe we have one of them in the reference. I will check that maybe during the break, but I can give you some references to learn more about data preprocessing. Okay, so this concludes our discussion on regression and basic machine learning pipelines. So now we are going to switch gears and look at another machine learning problem, which is classification. So before that, are there any questions so far? No questions in the chat, but I see the chat totally inactive. So do you guys still hear me? Okay. Okay, so okay, I can see the chat, so you can post your questions in chat if you have. Okay, so now let's switch gears and talk about classification for the rest of this time. Okay, so now we are going to consider a binary classification problem. Okay, which means I have two classes and I want to classify the given data point into one of the two classes. Okay, so now here is the example problem. So again, we are going to start with a synthetic problem. So throughout the course, we will do a lot of synthetic problems in class. Okay, this is mainly to make sure that I can visualize things and show you what happened. I think we have already given this warning before, but we are going to give in detail talk about this warning in the next lecture. Like the intuitions that we are developing in these 2D, 3D scenarios might not translate to high dimensional scenarios. But then we cannot visualize high dimensions, right? So we will stick to these toy examples in the class, but in your assignments, you'll be doing more real data experiments. Okay, so here's a simple two-class problem. Okay, so I don't have meanings for these classes. Let's just call them as blue class and orange class. Okay, so I have a blue class and orange class. Okay, now there are two features given as input. So there is x1 and x2. Okay, so the features or the input or x1 and x2, and I have given you here 100 examples per class. Okay, there are totally 200 examples here. Okay, now the first thing to do in classification is we know that we are dealing with mathematical models. So English words like blue and orange doesn't make sense. So we have to convert these classes into some numerical values. Okay. So now the first class, class 1 is blue and class 2 is orange. Okay. Now there are a couple of ways to convert these two numbers. For example, I could just call blue to be class 0, class value 0, and this to be 1. Okay, or I could also call this to be -1, this to be +1. These are two most preferable ways. You can do 1 and 2, but it doesn't make sense. You will see why. Okay, now I have a problem where there are 2 inputs and 1 output. Okay, now you can see that for the time being, let's take this way. Okay, I'm going to consider blue to be class 0 and orange to be class 1. Okay, now I have already mentioned this for the previous example, right? Like, so the first step in solving this problem is, can we reuse whatever we have learned so far? So if so, how?
No.
No? So we cannot reuse whatever we have learned so far here? Can you? Okay, so what we have learned so far? We have learned regression, right? So now the question is, can I use the regression model to solve this classification problem? Well, first question is, can I use the regression model to solve classification problem?
Yeah. Yeah.
Yes, you can, right? So I'm not asking about the quality of solution. Like, so once you decide that first class is 0 and the second class is 1, then you are predicting a real value. It's categorical. It's not 0.1, 0.2. It is just 0 and 1. But still, for the time being, you can just assume that this is a real number. And just off the shelf, apply linear regression to this, right? So now, so that is what the first solution we are going to see. Okay, so solution 1 is linear model. Okay, now I can just say that my y hat is going to be W0 plus W1x plus W2x2, right? There are 2 features, x1 and x2, right? So this is a linear model, okay? Now this is going to give me some number. Now the problem is this number need not be exactly 0 or 1. This could be any number, right? So I need some thresholding to decide which class it belongs to. So for 0, 1 classification, my y hat is going to be 1 if y hat is greater than or equal to 0.5, and it's going to be 0 if y hat is less than 0.5. Okay. Now what I have done here is I took a model that I already knew, which is linear regression. I repurposed it with just one extra condition on the top of it, right? Like, so whatever number linear regression gives me, I'm going to see if the number is greater than 0.5, in which case it's going to be class 1. If it is less than 0.5, it's going to be class 0. Okay. Now you can do the same thing for -1, 1 version as well. So if you consider -1 and 1 instead of 0 and 1, then y hat is going to be -1 if y hat is less than 0 and +1 if y hat is greater than or equal to 0. You can see that I put the equal sign wherever I want, so it's just approximate. Okay. So now let's just consider this version. Okay. In this case, why did I pick 0.5? So what is the significance of 0.5 here? Yep.
It's right in the middle of both values.
So it's right in the middle of both values, right? Like in some sense, it decides the decision boundary. Okay. So now the decision boundary for the first example is y hat is equal to 0.5. So I can draw a line which is y hat is equal to 0.5, and anything which is above that line is one class. Anything that is below that line is another class, right? Okay. So now we are seeing slightly different class of solutions, right? Like, so we did not care about what is above and below in regression, right? So now here is how linear regression is going to look like. In this case, I'm not using the bias term. Okay, so the model that I'm using here is y hat is equal to w1x1 plus w2x2. There's no bias. Okay, I solved linear regression, and this line that you are seeing here, right? So that is the line for this equation is equal to 0.5. So I believe you have seen how to visualize such equations in your Python tutorial. So if you missed the tutorial, you can go and see how to plot these kind of decision boundaries. Okay, so what I have done here is I first find W1 and W2 by using linear regression. Okay, and now I have W1x1 plus W2x2 is equal to 0.5. That is the line I want to draw. So you try different values of x1 and x2 that satisfies this equation. You plot it. Okay. Now anything that is above this line, right? They are all classified as orange class. Anything that is below this line, they are all classified as blue class. Okay. So this is the blue region, and this is the orange region. Okay, and this is the decision boundary, which is basically W transpose X is equal to 0.5. Okay, now you can see that, okay, first of all, is this a good model or a bad model? This is a good model or a bad model? Bad. So how much, like how bad? So it's really bad. Why? Because you see a lot of yellow dots in the blue region, right? Like, so which means that even in the training data, this model should have really, okay, first of all, what is the metric? What, like, we did not talk about it yet, right? Like, so what would be a nice metric for classification? Yeah.
Percentage of the orange in the orange class.
The percentage of correctly classified instances, right? Like, so, which is also known as accuracy. So in this case, what fraction of data points are correctly classified? You can see that there's actually a huge fraction of yellow, which is wrongly in the blue region, right? Now, we know one simple fix, which is to add a bias term, right? Let's see what happens if I add a bias term. So in this case, you see y hat is equal to W0 plus W1x1 plus W2x2. Okay. Now, you can see that suddenly things are getting a little bit better, right? Like it's not too good, like, but you still see, okay, so I should go to that screen because that is where Zoom people can see me. So you can see that there are still some yellow points which are misclassified, but the fraction of misclassification is probably less, right? Like, so I don't have an exact count, but it looks like qualitatively this is better than the previous one, right? Now, can we do better than this? Right? Like, this is clearly not the best solution. Like, well, of course, this is not even a direct solution. Like, we are reusing our solution from regression, right? Like, so now, can we do better than this? Okay. So we are going to see a new algorithm now. So just the second algorithm in this course. Like, so we are going to look at nearest neighbor classifiers or nearest neighbor methods. Okay. So the idea of nearest neighbors is really simple. Like the names are just it, right? Like, so now let's say I give you a new data point. Okay, so I'm going to give, okay, let's go to the original to avoid the confusions. Okay, now I give you a new data point. So this, okay, maybe I need a different color, which even people, okay, I hope this color is different. Okay, so okay, let's say I give you this green mark data point. Okay, now I want you to predict whether this is orange or blue. What would you predict? Would it be an orange class or a blue class? Orange, like, so what if my mark is here? What if my mark is here? What if my mark is here? Okay, what if my mark is here? Not sure, right? So now, what was your logic? So how did you confidently say blue and orange? Yeah, so you are implicitly looking at the neighbors in the region, right? Like, so you look at, if my neighbors are all orange, then probably I'm also orange, right? Like, so, or in other words, given a new test point, you look at the closest training points. Now you take a voting from the closest training points. Like, so if majority of my closest neighbors are orange, then I'm orange. If majority of my neighbors are blue, then I'm blue. Okay, very simple logic. But it's like, again, like one of the easy algorithms, but it works well. Okay, so now the intuition is clear. So let's try to formalize it mathematically. Okay, so I have to slowly swipe, because if I swipe a little bit fast, camera doesn't recognize it. Okay, so how do I formalize this mathematically, right? Like, so my prediction y hat of x, okay, is going to be 1 over k summation of xi belonging to the neighbors of x, y of I. Okay, where nk of x is basically neighborhood of x. So normally we will define neighbors by k closest points xi in the training data. Okay, now how do I define closeness? Any ideas? Euclidean distance could be one option, right? Like, so what metric to use to define closeness? Like, you can just use Euclidean distance. Okay, now this is only giving me average of predictions, k predictions, right? So now how do I change this to a classifier? This gives me an average number. For example, let's say let's say k is equal to 10. Okay, I see that there are 7 zeros and 3 ones surrounding me. What is the average? 0.3, right? So now would you classify it as class 0 or class 1? Class 0, right? So we can use a simple rule, which is basically if y hat of x is greater than 0.5, then it is class 1, and else it is class 0, right? In some sense, like, we're doing majority voting. Okay, now this majority voting is based on a very strong assumption. Okay, the assumption is neighbors look alike, or like neighbors come from the same distribution, right? So you are assuming that the class distribution is locally smooth. Okay, now if this assumption is false, then this is a bad classifier. Okay, let's say I have a data set where you could have orange points in the middle of all the blue points. Then this algorithm will not work, right? Like, so this is a very crucial assumption that this algorithm makes. Okay, this is for next week. Okay, so we're going to talk about assumptions of the algorithms. So we will also briefly talk about how you cannot come up with an assumption-free algorithm. Okay, so any algorithm should make some assumptions. Now, so this is where the idea of like picking the right model comes into play. Okay, so depending on the data set, some assumptions might be bad assumptions. So you should know what are the assumptions that are, just like how you should know what are the parameters and hyperparameters of the model, you should also know what are the strong assumptions that this model is making. Okay, in some sense, this is called the bias of this algorithm. This k nearest neighbor algorithm is biased towards data sets which has this locally smooth property. Okay, so we're going to call this as inductive bias of the algorithm, but you don't need to remember it right now. We are going to talk about it in detail later. Okay. Okay. So now we have a simple k nearest neighbor algorithm. Okay. Now, can someone tell me what are the parameters and hyperparameters of this algorithm? Any algorithm should have hyperparameters and parameters, right? Like, so what are the parameters and hyperparameters of this algorithm? Okay, so somebody says K in Zoom, but is it a parameter or a hyperparameter? Sorry? Hyperparameter. So K is a hyperparameter. You have to fix the K before you start the algorithm, right? Like you should first decide how many members are going to be in the neighborhood. Okay, that's an important hyperparameter. Anything else? Anything else? Yeah. Okay. So there is no parameters because nothing is learned per se. We are just using the training data directly. I'm going to come to that. But are there any other parameters? Okay, there's no parameter. Okay, but are there any other hyperparameter? There are some right answers in chat, but I'm going to leave it for the class to answer as well. So yeah. The type of distance metric, right? Like, so there are two hyperparameters here. So for K nearest neighbor algorithm, there are two hyperparameters. Okay, so what are they? K value and the Euclidean metric, right? Like, so you could use any other metric that you want. Okay, so in this case, we're using Euclidean. Like, what metric to use is a hyperparameter. Now let's talk about the parameters. Okay, so as you rightly said, I'm still trying to get names here. You're sorry, Theo. Okay, so as Theo rightly pointed out, like, so we are not learning anything per se, right? Like, we are just keeping the data and using the data to find the nearest neighbors. So there are no parameters per se, right? However, there is a small catch here. Like, so you are storing all your training data, right? Unlike linear regression, like where you find the parameters and then you can throw away the training data, in K nearest neighbor, you have to keep all your training data all the time to compute the nearest neighbors. So your training data are your parameters. In some sense, you have way too many parameters. Like if you have a million examples, you have a million data points in your parameters. Okay, so again, this is something that we will talk about probably a little bit later in detail. Okay, but just to know this. Okay, so now let's. Okay, once we know, okay, so for the purpose of today's discussion, we are going to keep Euclidean metric as such, okay? We're just going to vary the K value and see what happens. So here is the example when K is equal to 10, okay? So we are already seeing a lot of interesting things here. So when compared to linear regression, where you can only fit a line, right? Here you can see that you have this wiggly blue boundary, and within this wiggly blue region, you have another orange region. And similarly, you have a really complex orange region, and within that, you have an island of blue region, right? So this is a linear model or a non-linear model? Huh? Non-linear model. By just looking at the decision boundary, you can say that this is a non-linear model because you have non-linear decision boundaries, right? Like so. So this is a non-linear model, right? You have a lot of clusters forming here. Like so, you can see that, like when you have this small concentration of orange, this K nearest neighbor is actually capturing that. Similarly, you have a small concentration of blue points here, and K nearest neighbor is capturing here, right? Like so. Now, we are always interested in seeing what happens in the extremum, right? Like so, what happens if K is equal to 1? Any idea? Yeah.
That's a small region.
A lot of small regions. Like, can you say something about the training error and validation error?
0. Well, the training error is 0. The validation depends.
Good answer. So training error is going to be 0. Validation error, it depends. Okay. So here is how it's going to look like. Okay. So in this case, this is K is equal to 1. Okay. First of all, it's not a lot of small regions, like because whenever you see two orange, they are going to stick together. So it's kind of like it's still non-linear, like it's still quite complex. Okay, it's even more irregular than the previous boundary. Like this boundary is smooth, right? This boundary has sharp divisions, right? However, there are no misclassification here, as he rightly pointed out, right? Like, so you can see that whenever there is orange, that orange is an orange region. So training error, 0. But as we have already learned, this is not very impressive because we don't care about 0 training error, right? Like, so we care about the validation performance. So now let's try different values of K and see how the validation performance looks like. So here is what it looks like. So, okay, so we need to spend some time in understanding what is happening here. Okay, so now the straight lines that you're seeing are the performance of the linear model. Okay, now this is the linear train and this is the linear validation error. Now the other 2 lines are about the K nearest neighbor by varying different values of K. So when K is equal to 1, you get 0 training error, but very high validation error. Okay. What is interesting here is even with the worst possible K nearest neighbor, your validation error is actually very close to the validation error of the linear model. It tells you the power of nonlinear models. Okay, so you can actually get better than that. So as you try different values of K, you can see that probably the best value of K is here, right? So K is equal to 13, maybe, I'm just guessing. So the K nearest neighbor, the first observation is it's performing better than a linear model, which is kind of obvious because it's non-linear, right? However, it's kind of interesting that, like, on an average, it's actually better than the linear model. Okay, so now we have seen 2 classes of machine learning algorithms. In one extreme, we had least squares, which is like a linear model. In other extreme, like we have nearest neighbor, which can produce complex nonlinear boundaries, right? So now this tells you the landscape of algorithms that we are going to see in this course. Okay, so in one side you have least squares, and in other sides you have nearest neighbors. Okay, now in the case of least square, the decision boundary is very smooth, right? You had a line, simple. But in the case of nearest neighbor, the decision boundary is wiggly and it depends on a handful of data points and their positions, right? So the other way to look at this is linear models are more stable. You cannot change the decision boundary. Like it's not just decided by a handful of data points. It's not completely true. I will come to that. But in the other hand, like nearest neighbors, they are less stable. So why do I say they are less stable? Because let's go back to this place, right? I can actually put a bunch of orange here, then I'm going to have an orange island, right? Like, so suddenly the decision boundary changes, right? Like, so it's less stable. Now, they both have different types of assumptions. Can someone tell me what is the assumption? Well, we discussed in detail about the assumption of nearest neighbor, right? The assumption of nearest neighbor is it assumes that the class distribution is locally smooth, right? Now, can someone tell me the assumption of least square? What was the assumption? Yeah.
The class distribution is separated in distinct areas over the whole, area that.
Okay, I'll slightly rephrase it. So, but the answer is approximately right. So the answer is like a better like rephrased version of what he said is like you have this very strong assumption that the decision boundary is linear. You can have one line which separates the classes into 2 parts. It might not be true, right? Like so the linear least square assumes that the decision boundary is linear. Okay, in some sense, this is a very strong assumption. Okay, so the linearity assumption is really strong for most of the problems. So that is why non-linear models are preferred. Okay. However, to develop the theory, like we will start with linear models. Like, so probably we saw one nonlinear algorithm, nearest neighbors, but for at least for the next few weeks, we are going to focus more on linear models before we jump to nonlinear models. There's actually a question in the chat. What do you mean by locally smooth? So for people who don't remember the locally smooth assumption, like, so the fact that within a locality, like your class is identified by your neighbors, right? Like, so if you are surrounded by blue dots, then you are a blue class, right? Like, so this assumption is locally smooth assumption. Okay, now, in terms of terminology that we are going to develop in next lecture, okay, least square models are known for its high bias, okay, and low variance. I haven't defined what is bias and variance. Okay, so we are going, the next entire lecture next week is focused on bias and variance. But to give you some literal meaning or like intuition for what is bias and variance. Like, so when I say high bias, it means it has a very strong assumption. Okay. On the other hand, K nearest neighbor doesn't have a very strong assumption. Like locally smooth assumption is something that you will see in almost all the classifiers that we are going to discuss in this course. Okay. So they have very low bias. But low bias comes with a cost, which is they're going to be high variance because you can just move things a little bit. You're going to see different class versions. Okay. Okay. So I think we will stop here.